All right, so we're going to finish up chapter 7 this week. Okay, last two sections are 7.5 and 7.6. Okay, this section is on what they call sum and difference identities. Okay, most of what we do is going to be on those. There's a few other identities in the section, but we'll start with these. All right, let's take a look at this. Okay, I have on the left sine of x plus 3, and then versus sine of x plus sine of 3. Anybody think this will work? Like if I plug in a number for x, I get the same thing if I did it on the left and did it on the right. I think a couple people think it might work. What we can do is let's just graph it and see if they look the same. Before we even graph it, keep in mind this is a phase shift, right? This is going to shift it 3 units to the left. This is a vertical shift, right? When you take and you add a number, okay, sine of 3, it's just a number. Okay, pretend it's like 0.6. Okay, anytime you add a number onto the end, that's going to shift it up. Okay, so just kind of thinking about it that way, this is going to be a shift to the left. This one's a shift up. They're not really going to be the same. So actually, I don't even need to graph it. Right?
They're not.
Yeah, they're not going to be the same.
Yeah.
Yeah. All right, so the idea here is the distributive property doesn't work. Okay, you can't just say, oh, I'm going to distribute sine. Can't do that. Right, but there is a way we can deal with either having a sum or a difference. And that's the first few identities we're going to talk about. Okay, there's 2 for sine, 1 when you have a sum, 1 when you have a difference, and then 2 for cosine, 1 with a sum, 1 with a difference. They all look very similar. So what I would do is make sure you write them down, and you can use a reference sheet on the test describing. All right, I'm going to start out with the cosine difference formula. Okay, and all we have to do is keep track of kind of what goes where. Right? So let's say we had a difference of 2 things. Okay, in the last problem I had x and 3. Okay, and it was a sum. Well, this is a difference. All right, so the cosine of a difference is rewritten as cosine of the first argument times cosine of the second plus sine of the first, sine of the second. Okay, we might look at proving a couple of these formulas, but this one I'm not going to prove. It's a pretty lengthy proof. It is on page 409. But we're going to kind of use this as our starting point. Okay, we're just going to use that. Maybe we'll prove another one with it. Okay, so that's your cosine difference. If you want to write all these in the same space, there's going to be 3 more of these. So if you want to leave room, you can, or just kind of write them in your notes as we go.
Are they like the same length as that?
Yeah, they're exactly the same length. Mm-hmm. Sometimes it's a sum, sometimes it's a minus, and then you'll see they're very similar. All right, so I want to use that formula to try to figure out this, cosine of 15. Now, up until now, the only trig functions that we've done exact are angles that are multiples of 30 and multiples of what other number? 45. All right? So the trick here to figure this out is to rewrite cosine 15 as a difference. Okay? Write 15 as a difference of 2 numbers. But the numbers that you pick have to be multiples of 30 and 45. So for example, don't do 17 minus 2. Okay, we don't know how to work with a 17-degree angle in our head. We don't know how to work with a 2-degree angle. Okay, so we got to pick numbers that are multiples of 45 and 30. So what?
10 and 5, or talking about like what goes into like 2 numbers that like.
So multiples of 30, that's like 30, 60, 90,
okay.
120. And then 45, 90,
Okay.
135.
60 minus 30.
Well, you're on the right track. You're using the right multiples, but 60 minus 30, that would be 30.
30 minus 40.
Not 30 minus 45, but flip it around.
Yeah.
45 minus 30. And now what I'm going to do is expand it out using the formula. Now, the cosine of 45 and the cosines of 30 and the sines, those we should know. Okay, they have the square roots in them. We've gone through the special right triangles, but if you don't remember, I can kind of give you a hint how we can use the calculator to help us.
What do they have to be multiples of again?
These have to be multiples of 45 and 30. All right, so it says cosine of the first times cosine of the second. So it's cosine of the first, cosine of the second. Notice you just use what comes after the minus sign. So this is like my alpha, and this is my beta. Okay, I'm not using negative, it's not negative 30, it's whatever's after the minus. Plus sine of the first, sine of the second. So sine 45 times sine 30. Hey, any questions on that? Mm-hmm.
I'm still confused where to get 45 and 30 from the chocolates, the cosine of 15.
That you have to figure out two numbers in your head that subtract to give you 15.
Okay.
Yeah. Okay, and they have to be multiples of 45 and 30. So that's the easiest way to do it. So I can only ask you guys problems, bless you, about 15s. So you could do a 75, you could do a 15. You can't just do anything. Like I couldn't give you a problem about cosine 20. You can't get that one. Okay, so I got to give you certain numbers. All right, let's look at what these values come out to. All right, so cosine 45. That's 0.707. All right. Anybody remember what that is as an exact answer? It has a square root in it. Anybody remember when we drew the 45, 90 right triangle? What square root was involved here? Square root of 2. Yep, square root of 2 was involved. I think we had, I don't remember how we did it exactly. Yeah, we might have labeled, as long as you label these two sides the same, it doesn't really matter what size you use. It can be a big triangle, small triangle. Just keep these sides the same and then use the Pythagorean theorem. Watch what happens. 1 squared is 1. 1 squared is 1. Add up 1 plus 1, you get 2. And then take the square root. Okay? So just using your Pythagorean theorem, that's where square root of 2 comes in. But it's 0.707. The square root of 2 is 1.4. So what do you think this number is? It's the square root of 2. Yep, divided by 2. So that might be something you want to write down. Okay, when you see 0.7071, that's square root of 2 over 2. There aren't too many numbers that come up here, but 0.707 is one of them. Okay, cosine of 30. That one, that's 0.866. All right. So this comes from the 30, 60, 90 right triangle. 30, 60. Does anybody remember what square root is involved in this one? Not square root of 2. Or here's another one. Does anybody remember the relationship between the hypotenuse and the short side in a 30, 60, 90? It's double. All right. So what we could do is make this 2, make this 1, and then if you use the Pythagorean theorem, that would be square root of 3. Okay, if you square it, you get 3. Square 1, you get 1. 3 plus 1 is 4. Square root of 4 is 2. All right. So this one has to do with the square root of 3, and it's the square root of 3 over 3. Okay, let me just show you. Square root of 3. I'm sorry, square root of 3 over 2. Square root of 3 over 2. Okay, so 0.866, if you see that number, we got to write it as an exact answer. Okay, square root 3 over 2. And if you're dealing with 45s and 30s, these are pretty much the only numbers that are going to come up. Anything else that comes up is going to be a nice fraction. Okay, sine of 45, let's check that. Okay, so what is that one? That's the square root of 2 over 2 times the sine of 30. And that one comes out nice, 1/2. You could probably see where the 1/2 would come from if you did sine. Sine is opposite over hypotenuse, 1 over 2. Okay, any questions on going through that? All right, now let's just multiply everything together. Here we're going to have, what's the square root of 2 times the square root of 3? Square root of 6, and then 2 times 2, 4, and then the square root of 2 times the square root of 1, square root of 2, divided by 4. Okay, to add these up, we need a common denominator, but they already have it. So the final answer is just square root of 6 plus square root of 2 over 4. And you can't reduce that.
Why can't you add the square roots together?
It just doesn't work. Now, try like the square root of 16 plus the square root of 16. That's 4 plus 4, which is 8, which is not the same as the square root of 32. It just doesn't work. Right, and that's it. That's our answer. Okay. So what we can do to easily check it, just type in cosine 15. Now type this in. Make sure they come out the same. Okay, we've got square root of 6 plus square root of 2, and then divide by 4. Comes out the same. Right, so what this formula does is it gives us a way to find the exact answer for any angle that's a multiple of 15. So now we can do the 30s, the 45s, and the multiples of 15. And of course, there's a lot of overlap there. 30 is a multiple of 30. 30 is also a multiple of 15. Okay. Any question on that? If you don't have those two triangles, that might help you. If you have to find like sine, it's opposite over hypotenuse, or cosine, things like that. Otherwise, I would just memorize 0.707 is root 2 over 2, 0.866, root 3 over 2. With tangent, we might see another one come up, but that's basically what you need for this. All right. Okay, so this one says to verify that what's on the left and what's on the right here are the same. Okay, what we have on the left here is a cosine difference identity. Cosine, and then inside the argument, it's a difference. So let's just use our identity we just had. Okay, we're going to plug this in for the first angle. I think last time we used like 45. And you're going to plug that in for the second angle. That's where we plugged in 30. Okay, so we are going to plug a variable in. Okay. And when we're done, everything should cancel out, and we should be left with just sine. Okay, somehow. All right, so who can remind me what's my first argument going to be here? Cosine pi over 2. Okay, and what's going to come next? Cosine theta. And now is it a plus or a minus? A plus. So that you just have to remember. With the cosine difference formula, you use a plus. Okay? And then it's sine. What comes next? Pi over 2. And sine theta. All right. Pi over 2, that's obviously radians. What's pi over 2 in degrees?
90.
90. All right? So anytime I have an angle that's a multiple of 90, I think of the picture, right? Because that's either where it hits its highest point, its lowest point, or it's where it crosses the x-axis. So the only answers that can come up here are 1, -1, or 0. Okay, let's sketch cosine. Cosine starts at the top, comes down, and back up. So 0, 90, 180, 270, 360. All right, so when I'm at 90, what's my y value on that graph? 0. Okay, so cosine of 90, or cosine pi over 2, is 0. And now let's figure out sine of 90. Okay, sine starts here, goes like that. So 0, 90, 180, 270, 360. So what's the sine of 90? 0?
2.
Sine doesn't go as high as 2.
1.
1. Okay, so the highest value is 1, and when you're at 90, that's when you hit your highest. 180, you hit 0. 270, you hit -1. 360, back to 0. Okay, so this becomes 1. What's 0 times cosine? What's going to happen there?
0.
Yeah, this whole part just disappears. 0 times anything is 0. And all I'm left with is 1 times sine. What's 1 times sine?
1.
No, 1 times 1, that would give me 1.
Sine.
Sine. Okay, 1 times anything is just, stays the same. So 1 times sine is just sine, which is exactly what they said I should get. Great. Any questions on that? Okay, you could also use your calculator here if you don't remember the picture. But for me, I just visualize one of these two graphs, and then you don't even need to type it in. But if you type in cosine 90 or cosine pi over 2 in radians, you'll get 0. Sine 90, you'll get 1. Okay, any question on that? All right. So that's our cosine difference. Okay, we'll use that one to try to figure out what the cosine sum is. So this is our second formula of the 4 that are in this section. Okay, this is a fact we might have looked at, I think, back in chapter 6 or so. It was quite a while ago. But it turns out that if you want to take the cosine of a negative angle, the negative doesn't even make a difference. Okay, just to show you how that works. Take the cosine of 25, negative 25, it doesn't matter. So if you have a negative and you're taking a cosine, you can actually just get rid of it. Okay? With sine, it doesn't work the same. You can't get rid of it, but what you can do is just put it in front. Okay, you can't get rid of it because it does make a difference, but what you can do is move it to the front. Okay, so we're going to see both of these things happen in the next formula. All right. So we're trying to figure out the cosine sum. We're going to use what we already know. So my hint is to somehow write this as a difference. Right? If I had, let's say just something simple, 3 plus 2. The answer would be 5, right? How can you rewrite 3 plus 2 with subtraction and still get 5 as the answer? So yeah, 3 minus, what would you put right there?
Oh, -2.
Put -2. Okay, so now you just wrote addition as subtraction. Here's the first thing. There's the second thing. Because if you did this out, minus a minus becomes a plus. Okay, we're going to do exactly the same thing here. Okay, we're going to put alpha. And what do you think is going to come after it? Negative beta. Yep. So now what we're going to do is expand this out using the same formula we just did. There's your first angle, alpha. This time you are going to use the negative, okay? Because that comes after the minus sign. And once we do this out, we're going to have a formula for cosine sum that we can just write down and use it whenever we need it. If you didn't want to have to memorize cosine sum, you could do this every time. Just rewrite it as a difference and use that formula. Okay, but I think it's faster to just have one for a sum. All right, so we need cosine, cosine, plus sine, sine. Cosine, cosine, plus sine, sine. Okay, what's my first argument? Derek? Alpha. Yep. And my second argument. Okay, just be careful here what we write down. Cosine. Oopie? Negative beta. Okay, for sine, my first argument, alpha. My second argument, negative beta. All right, what did we say earlier about this negative inside the cosine? Does it make a difference? No. This negative with the cosine, we can just get rid of it. Okay? We don't even need it. So it's cosine alpha, cosine beta. Now, how about this negative with sine? Can I just get rid of this one? Matt, what do you think?
Move it to the front.
Right, we can't get rid of it, but what we can do is just move it to the front. So this plus is going to become a minus. And that's the cosine sum formula. The only difference is the plus changes to a minus. Okay, so cosine, cosine, minus sine, sine. And that's your cosine sum formula. Okay, based off the cosine difference, which is based off a proof we didn't do. All right, so now starting out just like we did with a number, I told you that the sum and difference formulas will allow you to do anything that's a multiple of 15. Okay, that says cosine 75. Now you can do this as a difference. Okay, some of you might be thinking you can find two numbers that subtract to give you 75. But I'd like to do this one as a sum. Anybody think of two numbers that can give me a sum of 75, but they have to be multiples of 30 and 45? Don't think too hard.
30 plus 45.
Just 30 plus 45, yeah. Did anybody think how to get 75 as a difference?
270 and
90, that's true. It is 90 minus 15, but generally we want to try to work with angles that are multiples of 30 and 45. About if you did 135 minus 60. 135 is a multiple of 45. 60 is a multiple of 30. So if you wanted, if the test didn't say how to do it, you could do this as a difference. Okay? But we're going to do it as a sum. Any question on that? Any difference? It just takes practice to figure out how to do that in your head. All right, so we've got cosine, cosine minus sine, sine. So cosine, cosine minus sine, sine. Okay, and we got to write all these as exact answers. Okay, so we put up cosine 30. Okay, somebody remind me what that is as an exact?
Pi over 2 over divided by 2.
Not pi.
That makes sense.
Yeah. Square root of 3 over 2. Okay, square root of 2 over 2, you're going to see that one right now. Cosine 45, that's the 0.707. That's root 2 over 2. Does anybody remember the sine of 30? This one came out nice. Not 1. 1/2. And how about the sine of 45? We did this one when we did the first problem. Yep, that's also the square root of 2 over 2. So we're actually going to get the same answer as we did when we did cosine 15. It's just the plus changes to a minus. So square root 3 times square root 2 gives me square root 6. 1 times the square root of 2 is square root of 2. And they both have a denominator of 2 times 2. 4 and 4. And that's the exact answer for cosine 75. Okay, any question on that one? So the test you're going to have, I think there's 3 problems that start out just doing numerical kind of stuff like this. And then there's there's 2 verifies on the test. Okay? So a problem like a verify wouldn't be a multiple choice. You just have to show me. This is all the work you'd have to show right here. Okay. All right, so since we did a lot with the cosine, we're gonna jump to the sine. Okay, and rather than go through the proofs of these, we could, just like we did with the last one. I'm just gonna give you the last 2. Okay, so the sine sum formula. Okay, it's a little different. Okay, it's sine cosine plus cosine sine. So sine of the first, cosine of the second, plus cosine of the first, sine of the second. Okay, what is nice with the sine formula, if you're doing a sum, you use a plus sign. If you're doing a difference, you use the minus sign. Okay, so that part kind of matches up, unlike the cosine formulas. Right, and then your sine difference formula is sine of the first, cosine of the second, minus cosine of the first, sine of the second. Let's see, I'll go right back to that. Okay. Right, and these formulas would allow us to do exactly the same kinds of things we did with cosine. You could find the sine of 15. You could do sine 75. Okay, I'll just make one up we haven't done yet. Let's do 105. Okay, we'll do the sine of 105, and I will tell you it can be done either way. You could find 2 numbers that add to 105 or subtract. Does everybody have the top one? Okay. Anybody give me a way to write 105.
Equals 15.
We got to stick with numbers that are multiples of 30 and 45. That is true.
60 and 45.
Yes, you could do 60 and 45. Okay, or, can anybody think of a way to write 105 as a difference? Yep.
135 minus 30.
Yep, 135 minus 30. It does not matter which way you do it.
That's 45.
Think 30. It'd come out the same either way. Okay. Does anybody want me to go through doing one of these two ways? Yes?
You say you're doing one of each?
You want me to do the top one?
Sure.
All right. So if we're going to do that, that's a sine sum. Okay? So, sine of the first, cosine of the second. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. Cosine 60, sine 45. Okay, and if you have all these memorized, you can just fly right through it. If not, you can look up the sine of 60. That's root 3 over 2. That's root 2 over 2. Cosine of 60 is a half. Sine of 45, root 2 over 2. So you see the square root of 6 comes up here, denominator of 4 comes up a lot. Just that's the kind of problems we're doing. So it's square root of 6 plus square root of 2 over 4. Okay, and if you want to check and see, make sure you're good problem to prepare for the test. Try doing it as a difference. Make sure you get the same answer. You will. All right, so there's our sine sum and difference. Tangent sum and difference not used as much. Okay, I'm going to give the formulas to you just so you have them, but I don't think we're going to do an example with them. Unless you want to see one, I can make one up and do one. All right, so a little more complicated than sine and cosine. Okay, tangent of a sum is tangent of the first plus tangent of the second divided by 1 minus tangent of the first, tangent of the second. And then tangent of a difference, it's basically the same thing, it's just the pluses and minuses switch. Okay, so tangent of a difference, tangent first minus tangent second, over 1 plus tangent first times tangent second. Okay, and maybe I'll do tangent 15. Okay, I'll just do a basic one so you can see how it works. So I said I was going to do tangent 15. I think the easiest way to write it, we've done this already, 45 minus 30. All right, we'll fill it in and see what happens. So you're going to get tangent 45 minus tangent 30 over 1 plus tangent 45, tangent 30. So we'll just go through these numbers and see what happens. Okay, tangent of 45, that answer comes out really nice. Does anybody remember what the tangent of 45 is?
Root 2 over 2.
Actually, we don't get a decimal here. 1. Yeah, it comes out to 1. If you just type it in, 1. So 1 minus. Okay, does anybody remember what this number is? I accidentally, I said this one earlier and I meant root 3 over 2. But this one is root 3 over 3. Okay, that's the other special number that comes up, and you only see it when you do tangents. 0.577, that's root 3 over 3. Okay, 1 plus, what was the tangent of 45? 1, and the tangent of, what's tangent 30? Root 3 over 3. All right, and that's basically the answer. The only thing they might do, because that's a little messy, is if you triple everything in the top and triple everything in the bottom, okay, using distributive property, it's going to get rid of these denominators. Okay, so what you'd end up with here is 3 minus the square root of 3 over 3 plus the square root of 3. That kind of cleans the answer up a little bit. And we could even go further if you multiply top and bottom by the conjugate, but I'm going to stop with that. Okay, I would at least like you to get rid of the fractions if that happens. Okay, so it's a little cleaner. Yeah?
No, because I got confused and I thought that the tangent of 45 equals 1, but I forgot that you multiplied by the square root of 3 over 3.
Yeah.
So I thought it was supposed to be 2 plus square root of 3 over 3, but now I just...
Yeah. Okay, so that's a good one because you saw 0.577. We hadn't seen that number yet. Okay, so make sure you remember that that's root 3 over 3. All right, the other identities we're going to look at, we're not going to prove any of them. Okay, I'm just going to give them to you and we'll see how they work. All right, this does not work. If you have a 2 next to the x, you can't just take the 2 and put it in front. First of all, putting a 2 in front, that's an amplitude change. Makes the graph taller. Putting a 2 inside stretches or compresses horizontally. Okay? So this is a horizontal stretch on the left, or actually that's a compression, and this is a vertical stretch on the right. So there's no way, even if you graph them, they're not the same transformation. Okay, so they're not the same thing. But that's what sine 2 theta equals. Somehow it equals 2 sine cosine. So if you want to get rid of this 2 next to theta, you can do it, but look what happens. It gets kind of complicated to get rid of the 2's next to thetas. Can anybody think of a way you can write 2 theta? Think of like, what calculation would you do to get the answer of 2 theta? Not theta times theta, that would be theta squared, but you're on the right track. Yep.
Is it sine 2 plus sine theta?
No, not quite. Think like an algebra, like if you got an answer of 2x after combining like terms. Think of which.
Beta.
Yeah? Yeah. If you had theta plus theta, that's 2 theta. Now, what is this thing on the left called? This is your what? So this part's the argument, and what do we call this identity? This is the sine sum identity. Let's plug into the sine sum identity and see what happens. Now, it's theta and theta, so the arguments are the same. So it's sine of the first, cosine of the second, but they're the same thing. Sine of the first, cosine of the second. And then cosine of the first, sine of the second. But again, they're the same thing. So it's cosine theta, sine theta. Yeah. Plus cosine theta, sine theta. And now in the first part, we have a cosine times a sine. In the second part, we have a cosine times a sine. How many cosine times sines do we have? One of each. So we have a cosine sine, another cosine sine, for a total of 2 of the cosine sines, or sine cosine. You can switch the order. That doesn't matter. Okay, in fact, you know what? We don't even need parentheses if we don't want. Okay, it's kind of like if I said, well, you have x times y plus another x times y. How many x times y's do you have? You have 2 of the x times y's. Right? Same thing here. Sine times cosine, another sine times cosine. We've got 2 of the sine times cosines. Okay, so that's what we call a double, because of the 2, a double angle identity. Okay, sine 2 theta equals 2 sine cosine. And out of all the double angle formulas, it's actually the only one that I have memorized. Okay, if I need the cosine one or the tangent one, I have to just look it up. Okay, and that's all you'd have to do with this too. Okay, that's one way you can write cosine 2 theta. Cosine squared minus sine squared. Looks similar to something we might have studied before, but it's not. Okay, if you remember looking at the Pythagorean identity, sine squared plus cosine squared, this is a minus. Okay, so it's a little different. Or you can write it that way. Or you can write it that way. Which one you'd use, it really doesn't matter. They're all the same. Okay. If I was doing a problem that said rewrite the following in terms of cosine only, well then I'd probably pick the bottom one. If it said rewrite in terms of sine only, then I'd probably pick the second one. Okay, but they're all the same. It doesn't matter which one you use. Okay, and tangent 2 theta is 2 tangent theta over 1 minus tangent squared. Again, we're not even going to explain or go through the proof of why that's true. I'm just going to give it to you. But I would say the most important ones to know, those 2. I'm giving you the tangent ones just for the purpose of having your notes complete. But in this class, we don't really do a lot with any of the tangent ones, if anything at all. Okay, but at least make sure you copy down the first 2, sine and cosine. All right, so this problem, what they want us to do is just rewrite what they've given us. 2 cosine x plus sine 2x, using only x's in the argument. You can't use a 2. Okay, I want to get rid of that 2 somehow. All right. Now, if you look at the first term, does that fit the description of what they're already looking for?
Yeah.
Yeah, that's fine. It just, there's a 2 in front. We don't care about that. We just don't want a number inside next to the x. So leave the first part alone. It's the second part that has a problem. Okay. How can I rewrite sine 2x? Getting rid of that 2. That's part of it. 2 sine x. One more thing. Cosine x. Okay. So now we've done it. We've gotten rid of the 2 from next to the x. The only way to do it is to use one of these formulas. That's the only way. And now, what do this term and this term have in common? Yep, they both have a cosine x. Anything else? A 2. Okay. What are you left with if you factor out a 2 cosine x from that first term? Yeah, just a 1. Because if you distributed it back out, you'd have 2 cosine x times 1, which is 2 cosine x. And what about if you factor out 2 cosine x from the second term? You're just left with sine x. And of course, you can check it just by distributing it back out. Hey, any questions on that? Yeah.
So I'm confused on how you got the final answer.
This answer?
Yeah, I didn't know.
So since there's a 2 cosine x here and a 2 cosine x here, we factored out what they both had in common. So you write that on the outside. And then in your parentheses, you have to think about, if I were to distribute, how would I get back to what I started with? 2 cosine x times 1 is 2 cosine x. And 2 cosine x times sine x, if I distribute it out, is 2 cosine x times sine x.
Oh, so you just take out what they both have in common?
Yeah.
The points as a parentheses, what you need to go back to the original?
Yeah, it's basically exactly like factoring this problem from Algebra 1. You'd say, well, they both have a 2. They both have an x, so I can factor out a 2x. If I factor that out, that leaves me with a 1. And if I factor it out here, it leaves me with a y. Same idea. Okay, any other questions on that?
Why did our proof that in the end, in the first place? Did you see that proof? 2 times?
How did we get the
The cosine. Cosine.
this cosine?
Yeah.
That comes from right there. So if you want to replace sine 2x, you have to replace it with 2 sine cosine. That cosine is that cosine right there. I used x's in the identity, I used thetas. That doesn't matter. Any other questions on that? All right, so let me give you about 20 minutes or so to start the homework. So if you have questions, you can ask me. Okay, so the homework is on 417. It's 2 through 5, 9, 10, 17, 18, 29, 31, just part A. Don't do part B. And 37 and 41. Okay, if you need a book, there's some on the back counter. And I'll walk around and help you guys out and answer any questions.